Hi. If you have ever tried to run a high-pressure RTM simulation, you probably know that, apart from the cost, setting up the license and software is a project for itself. Composites on Clouds is our response to this problem. We are PhD students at the University of British Columbia working at Composites Research Network. Composites on Clouds is created for 2019 ASC Software Simulation Challenge. And here, in this video, we are going over the features, workflow, and verification test cases for our tool. We will also show you how to use Composites on Clouds to run an RTM simulation. Composites on Clouds is a web-based open-source finite element tool for prediction of filling time and filling pattern of composite preforms in high-pressure RTM processes. There are 5 steps between you and submitting and visualizing the results. First, you need to create the mesh. The mesh should be in UNV file format, which can easily be created in Salome, a pre-processing open-source finite element tool. Then, you upload the mesh in our servers. Our tool will process the mesh and shows the geometry, boundaries, and sections to you. If you confirm the mesh, then you can define the problem data such as resin viscosity, preform properties, solver properties, and boundary conditions. Then you will submit the job, and we will use Phoenix, a powerful open source finite element tool, to solve the RTM simulation. When the job is finished, we even embedded an open source post-processing tool so that you don't need to export the results. But if you need the files, you can easily download them in your browser.
Composites on Clouds is developed in Python and uses 4 major open source packages to create a user-friendly experience. Phoenix is the beating heart of our solver, which processes the discretized geometry and solves the partial differential equation with the given conditions. Django is the backend for the server and web interface. Apache and Paravio are well-known tools that we use for post-processing and visualization. What's behind the scene? User sends a request, which includes the mesh file, material definition, boundary conditions, and solver settings. This is a step-by-step wizard developed in Django frontend. Once the server receives data, it converts the mesh to a Phoenix-friendly format and saves it on database. Additionally, all other user inputs are processed and stored in the related tables on the database. When the user submits the simulation, Phoenix reads the data from database, creates a model, solves the partial differential equations, and stores the results in a specific folder created on server for the given simulation. For post-processing on data on the web, we implemented Apache to run a Paravio server. Paravio client is embedded on a web page that delivers the results to the user in an interactive way.
One of the methods in the literature to simulate RTM processes is control volume finite element method. Like any other finite element method, the domain is discretized in the first step. Then, a representative volume is assigned to each node. The method to calculate the representative volume is shown here. A saturation value is assigned to each node, which is 0 as the start of the analysis. Currently, we use 2D and 3D shells as finite elements. An available region is defined which consists of the elements right beside the inlets at the start and next to the field nodes in later iterations. In each step, the pressure is solved in the available region and velocity is calculated based on the Darcy's law. Velocity flux of resin to the nearby CVs. The time step is calculated in such a way to fill 1 CV at a time. And the saturation of each cell is updated based on the flux rate and the size of the time step. At the end of each step, the available region expands based on the new saturation value. In our brief search in the literature, high-pressure RTM is either achieved with a distribution medium, where the chance of fiber wash is low, or without the medium, where the shape of the part should be designed carefully to prevent fiber wash. In the former case, user can create a stack of preforms including the distribution medium, and the total permeability is calculated as an averaged value for the whole stack. In the later case, Composites on Clouds finds the height of each node during the analysis. This output helps the designer to prevent fiber wash. Composites on Clouds has several features which are shown briefly in this slide. Let's simulate filling of a bipolar section now.
When you enter the Composites on Clouds website, you will see the main page, which includes a link to the application and some information about the software. In the About section of the web page, there is a link to the documentations on GitHub. At the bottom of the page, you can find our contact details in case you need further information or support. So let's run the application. Here, you can create a new analysis or continue to work on the previous analysis. All the previous analyses are listed on the right-hand side. Just click on the name and it redirects you to the page where you can continue to work on it by confirming the mesh. For creating a new analysis, simply give it a name and a short description. Then hit the Create button. In the mesh page, you need to upload the mesh. Currently, only UNV format is supported. When you hit the Upload button, the file is transferred to the server. Server reads the mesh and converts it to a Phoenix-compatible format to be stored on the database. When the uploading and converting process is done, it automatically redirects you to the mesh display page, where you can see the uploaded mesh with different faces and edges that are highlighted with colors. A bounding box is included to make sure that the uploaded mesh is on the correct scale. Moreover, the graph is interactive, so you can rotate, zoom in and out, or pan every corner of the mesh. If the mesh is not correct, you can upload it again. Otherwise, just hit the Confirm button to go to the next step. Here you specify the resin viscosity. All units, including the unit of viscosity, are arbitrary as long as they are compatible. In the next page, you can create as many preforms as needed for your simulation. Give it a name and define its thickness, fiber volume fraction, and permeability constants in different directions. You can delete the created preforms by this little cross button next to them, or update them by putting their name in the name section and giving them different values. In the section page, you can stack the preforms on each section with varying angles. You can remove the created sections using this cross icon similar to the preforms. Each section has to be associated with at least one preform in order to proceed to the boundary conditions. There are three types of boundary conditions available: wall, where the normal resin velocity is 0, inlet, where you can set the resin inlet pressure or flow rate, and outlet, where you can adjust the outlet pressure. A list of assigned boundary conditions are shown on the right-hand side of the web page. You can easily modify the boundary conditions if there is a mistake by selecting it on the left menu and altering the related inputs. In the step page, you can define the solver parameters. You can choose Fill Everywhere or Fill the Outlet as the termination type. If you choose Fill Everywhere, the solver stops when all cells are filled with resin. If you choose fill the outlet, the simulation will be terminated if the resin reaches the outlet that you have specified in the boundary section. The end time can be specified to terminate the solver if none of the conditions is satisfied in the given time. Output time step determines the frequency of writing output. Maximum iteration number, maximum idle iterations, and minimum saturation change give you more control over the solver. You can see the overview of your inputs at the submit page. You can download the UNV or converted XML mesh file. The configuration file, which includes all of the inputs, can be downloaded from the link here. This file is similar to the file in terms of usage and can be used to redo the simulation in the future versions. If there's a mistake with the input data, you can easily go back to the related page to modify the input using the sidebar. The sidebar gives you the ability to quickly review the mesh name, resin viscosity, created preforms and their thicknesses, define sections, and boundary conditions. If everything is okay, you can submit the job to start the simulation. The status page provides you with some details about the solution progress and warnings for various conditions that might happen during solving. You can terminate the process simply by hitting the Kill Job button. Once the simulation is completed, you can view the results and post in your browser. Once the preview is loaded, click on the paper icon where you can access the result files of your analysis. Boundaries, domains, and materials activity files are for software debugging purposes. A log of events are also written in a message file, which can be downloaded here. Flowfront versus time.pvd file is a contour that shows the position of the flowfront at all time steps in one figure. High-pressure.pvd shows the maximum pressure that each node experiences during the filling. To check the pressure distribution, saturation, or the velocity field at each step, open filling medium.xdmf. You can have a nice animation of the filling pattern right here in your browser. In case you need these files offline, just click on the download links below.
Now that you have seen how this tool works, let's go over the documentation of our tool and some of the test cases. Composites on Clouds is available on GitHub. We will be happy to get your feedback and welcome you to contribute to this project. We created a wiki on GitHub as well, which will be updated and expanded as needed. We uploaded some test cases and some examples. We aim to add more verification cases as we move forward to test the solver and platform in different situations. But for now, let's go over a 1D and a 2D test case. The mesh for all test cases are available on GitHub. In the 1D test, we use a rectangle, 1.5 meters long and 0.2 meters tall. The viscosity is 0.01 Pascal seconds, and we create a preform with 0.02 meters thickness and 0.2 volume fraction of fibers. We set K11 to 1e-8 square meters, and K22 is 0 to have a 1D diffusion problem. We have an inlet with 100,000 Pascal pressure and an outlet with 0 pressure. The other edges are wall. When we submit the job and wait for the success message, we can check the results. If we compare the result of the 1D analysis with the analytical solution of this problem, we can see that the filling time is pretty close. We think that the difference might be due to the mesh size. The 2D test case verifies the implementation of anisotropic permeability. Here, the model is a 1.2 times 1 meters rectangle. You can find the mesh in the GitHub repository. Enter 0.02 Pascal second for viscosity and create a preform with the data shown in this figure. In the section page, assign this preform to all domain and rotate it by 45 degrees. The corner edge is the inlet with 100,000 pascals pressure and all other edges are wall. These boundary conditions will eliminate the chance of dry areas. Our solver assumes zero pressure for the flow front. The results of this case are compared with the results of a well-known software for RTM processes, LIMS. As you can see here, the shape of the flow front and the fill time are very promising. We have several ideas to further develop this tool, some of which are shown here. Please contact us if you have any question, feedback, or if you want to contribute to this project. Thank you.